Thank you very much. Hello and welcome to Imperial College and the Great Exhibition Road Festival. Thank you very much. Hello and welcome to Imperial College and the Great Exhibition Road Festival in London. I'm Kevin Fong. This is the BBC World Service, and we're here with our partners, the Royal Commission for the Exhibition of 1851, to discuss space exploration with some of the world's leading spaceflight engineers. Almost exactly 50 years ago, Neil Armstrong and Buzz Aldrin landed their lunar module Eagle on the moon, and humans set foot on the surface of another world for the first time in the history of our species. It is one of humanity's greatest achievements, an endeavour that captivated the world, a signature moment in what we've come to think of as the first space age. And while it's been some time since we put an astronaut on the moon, we never stopped innovating or exploring. Right now, we're in the midst of a particularly fascinating period for spaceflight and space engineering. NASA has peppered the surface of Mars with landers and rovers. India has discovered water on the moon. The European Space Agency has an ongoing mission to Mercury, and, perhaps most intriguingly of all, private enterprise has developed technologies that have the potential to revolutionize the field, from space planes and advanced engines to inflatable space station modules and reusable rockets that can fly themselves back and make a soft landing. We might think of this as a second space age, and our guests tonight are at the forefront of it, making the technologies and engineering that will one day take us to the edge of possibility in outer space. Please welcome Adam Steltzner, NASA's chief engineer for the 2020 mission to Mars, and the person who masterminded the landing of the Curiosity rover on the surface of Mars 7 years ago. Anuradha TK is the GeoSat program director in charge of launching satellites for ISRO, the Indian Space Research Organisation, providing tele-education, internet access, and importantly, disaster management. David Parker, formerly a genuine rocket scientist, is now Director of Human and Robotic Exploration at the European Space Agency. Please join me in giving them a round of applause. Now let's start with you, Adam. You're chief engineer on one of NASA's flagship missions, Mars 2020, an impressive job title with a list of achievements in space exploration to match. But it wasn't always clear that your career was going to be quite so stratospheric, was it? Tell us about Adam Steltzner and the moment that changed it all for you.
All right. Thank you, Kevin. I was not always interested in space, or certainly not in physics or science or engineering. I was a poor student, to be honest, in anything I studied. And in the US, we have high school, which ends at about 18. And it ended, but not successfully for me at that age. And I was playing rock and roll around the San Francisco Bay Area, looking to become a rock star. I wasn't a very talented musician either, unfortunately. And one night, returning home from playing a gig, a show, I noticed that the stars were in a different place in the night sky than they had been when I first went out to load into the show. I clearly had missed that whole Earth spinning on its axis thing. But I became curious about the apparent motion of the stars in the night sky. And I followed my curiosity to a local community college, one that you didn't need to have good grades to get into. And that spark of curiosity resulted in a fire of exploration that burned across my life, changed the course of my life, and now has me working on putting stuff on Mars.
Thank you. Now, Anu, you are another space explorer, but you're the most senior woman at ISRO. You oversee the launch of satellites into high orbit around the Earth, upon which our digital communications and our digital lives on Earth depend. So just give me an idea of the sorts of things that go into preparing these missions.
Any of these satellites, they take about 4 years if they are totally new satellites. If it's a repeat satellite, it may take about a year to prepare it. So, satellite consists of many smaller electronic systems, mechanical systems, thermal system. All these systems have to undergo their own tests at subsystem level. Then once we bring them together, start building them up into a satellite. Those satellite also will have to undergo a whole lot of tests, electronic tests, and you have to put them in the environmental conditions like it is in space. You have to create vacuum, put the satellite, and make it go up and down in the thermal cycles, and you have to make it vibrate and see that it withstands all the vibration effects during the launch. And after going to the launch pad, we have several parallel activities. One for the fuel filling, one team will be working. Other team, it will be unpacking the satellites and then do certain mandatory checks because this is the last time we are going to test the satellite. And we have to have all the interface checks with the rockets. And the launch day, yes, no need to cross fingers. We'll be confident that everything is going to be fine.
And it's interesting that you say that. I mean, I've been there for the preparation of these rockets, but actually my experience is that, everyone who knows what's going on ends up crossing their fingers and holding their breath. I mean, David, you're now involved in spaceflight more from the strategic and political view these days, but you have a background in propulsion engineering, so you're well placed to explain why it is that actually there often are some nervous people around launch day.
Of course, it's a launch date is the culmination, Kevin, of a huge amount of work that's just been described, years and years of work, and you've taken this beautiful flower, this delicate satellite, and you're going to put it on top of 700 tons of high explosive and press a button. So wouldn't you be nervous? Yeah. And it's even more nerve-wracking when it's not a delicate satellite, but it's 3 human beings. Going and seeing astronauts launched on Soyuz vehicles in Kazakhstan, as I'll be doing in a few weeks' time to see a European astronaut being launched. That's a very special moment. And they're launching from the same launch pad the Gagarin launched from. So it's also another step in history for each of these astronauts.
Now, before I come back to Adam, I just wanted to divert a second to talk to Anu really about one of those delicate flowers, as David describes them, launching on these rockets. And your particular satellites have a specific destination in mind. You put them up into something called geostationary orbit, which keeps them in a fixed position over the same point on the surface of the Earth 24 hours a day. Just tell me a bit about that and how you do that and why you do that.
So a satellite which is placed at 35,786 kilometers above the mean sea level, it will have the same orbital period as the Earth. Why is it important? Is because all the ground antenna, they are continuously seeing the satellite. There is a continuous line of sight between the satellite and the ground. So the most ideal thing for the communication purposes, for even the weather monitoring. So what we do is when we launch these satellites, so part of the energy is given by the rocket and it will put it in a highly elliptical orbit, and subsequently the satellite carries a small engine itself called the liquid apogee motor, and we keep firing them to make it a circular orbit and go to the exact longitudinal position. That is the final point, and of course later on you have to keep within its house a window within the orbital period.
And just give me an idea of how high these satellites are. Now, space station is in what we call low Earth orbit, isn't it? About 240, 250 nautical miles, so about 400 or so kilometers. Where are these geostationary satellites?
These are at 35,786 kilometers. Like the small low Earth orbits, you can have from 200 to 1,000 kilometers, 1,500 kilometers, you can have satellites. But they will have a rotation with respect to Earth, so that they will cover a particular area at a particular instant of time and they move away. Whereas at this 35,786 kilometer, it moves along with the ground point.
perfectly in sync with the Earth.
Yeah.
Perfect. Now I want to come to Adam, because we've talked a little bit about launch, about what happens when you get there, but they always told me that the hardest 2 feet in all of spaceflight are starting and stopping, and I want to talk about the stopping and how, because you were involved in the entry, descent and landing of Mars Curiosity in 2012. I listened to it not far from here in the Natural History Museum, to the live audio of that landing, and for me it was sort of a nerve-wracking moment as you heard all those separate systems coming into play to try and get Curiosity onto the surface of Mars. Fantastic moment, but you were part of that mission. So how fast was Curiosity moving as it came into Mars's atmosphere?
Well, it was going a little bit over 13,000 miles an hour, a little bit under 6 kilometers a second.
So hugely quick, and the problem is that you can't slow down a vehicle coming into the Martian atmosphere in the same way that you can slow it down if it's coming into Earth. Why not? Why is it harder on Mars?
Well, so Mars has got a very thin atmosphere, about 1/100th of that on Earth. And you arrive with enough speed, enough kinetic energy that the energy of motion could melt or vaporize the entire spacecraft. And that, in generally, of course, is considered poor form. So we need to manage that. We put the spacecraft in a special aeroshell. We coat the aeroshell with a material that will smolder and will not burn. And we essentially shed that energy of motion to the atmosphere of Mars, kind of burning a hole in the sky of Mars as we slow down. That process takes us down to about 1,000 miles an hour or so. Still not slow enough to land on the surface of Mars, so we opened up a parachute. In our case, the world's largest supersonic parachute, just under twice the speed of sound, Mach 1.7. Gives us a neck-snapping 12 Gs of deceleration. The parachute, again, slows us down well, but we're on Mars with this very vaporously thin atmosphere, and so no parachute we can put up will take us down to a sufficient speed to solve the full problem, so we need to let go of the parachute and go into rockets. Every successful expedition to the surface of Mars has used those 3 pieces of the puzzle. But then there's a last piece of the puzzle. You're left with a last bit of air velocity you need to take out with a landing system, a touchdown system.
And this is the piece of the puzzle that I love the most, and it's the piece that you were in charge of in 2012, right? So this is the so-called sky crane. Now, I remember the first person to explain the sky crane landing system to me was not a scientist, wasn't anyone who had anything to do with spaceflight. And when they described it to me, I thought, you've got to be wrong. That's just a crazy system. So just tell me about that system.
Right. I mean, I have to share with you that when we first told the head of NASA, the NASA administrator, Mike Griffin at the time, the leader of NASA, what we were planning to do, he also said it was crazy. So it is a little bit crazy. It is also the least unacceptable solution that we could come up with. The notion of the sky crane is that once we've flown out all the speed we can with the parachute, we go onto rockets, we've got a jet backpack, a propulsion system we call the descent stage, attached to the top of our big, beautiful rover, Curiosity. And we flew as a single unit, a single body, down to about 22 meters above the surface, and then released the rover below its jet backpack and lowered it down to a point 7.5 meters below the descent stage, and the two continue down until the weight of the rover is taken up by the surface of Mars. At that point, we cut the descent stage free and we fly it off to a safe distance, some 650 meters or so away from the rover. Easy. But it looks crazy.
I mean, it is a crazy scheme. I think if you've seen that in a science fiction movie any time before, you'd have thought that's just ridiculous. But I mean, if that doesn't sound science fiction enough, David, you spent a huge part of your career, 20 years or so, involved in the Rosetta mission.
Absolutely. Rosetta is also an extraordinary mission because to imagine trying to design a spacecraft that could fly halfway across the solar system to an object that was only 20 kilometers across, not just find it, go into orbit around it, actually an object that has almost no gravity, and furthermore try and put a little robot that weighs only 100 kilograms onto its surface. seemed impossible challenge for Europe to take up in the early 1990s. So it was 10 years of thinking and designing, building, and then 10 years waiting as it travelled across the solar system. And then an incredible day in November 2014 where we released the probe and waited to see what happened. And Philae, the little probe, made its bouncy landing, but started to relay back some fascinating information about what is kind of a fossil of the beginning of the solar system. Comets are the kind of leftover builder's rubble from when the solar system was built, and maybe they tell us about what the solar system was like at the beginning, and how water got to our own planet.
And all of this fundamentally is about defeating gravity in the right way to move huge distances across our solar system to get into the right orbits. Just explain to me a bit about what gravity is, why it's so problematic for you, and what role orbits play in all of this.
Well, it's a complicated challenge because when you try and describe what you mean simply by being in orbit, for example, around the Earth, you've got to get this 7 kilometers a second to be in orbit. Sometimes people describe it as escaping Earth's gravity. You're not. You're completely controlled by the gravity of the Earth when you're flying around the Earth. But indeed, to get to another place in the solar system, to get to Mars, to get to a comet, you have to escape the immediate gravity of the Earth and head outwards. So you need a lot more velocity, yet again, and maybe another. You need to get 11 or 12 kilometers a second to escape from the Earth and head off. To do that requires a lot of fuel. So with Rosetta, more than half of the weight of the spacecraft, the mass of the spacecraft at takeoff is fuel. But even that is nowhere near enough to get where we wanted to go to. So we use a trick. And the trick is the famous gravity slingshot. The technique actually invented by a guy called Giuseppe Colombo, we may come back to, an Italian engineer working for NASA in the 60s and 70s. And what you're doing is playing a game with the rest of the planets in the solar system. So that Rosetta, it actually headed off into space and then came back to the Earth and used the gravity of the Earth to turn itself, and in so doing exchanged a little bit of energy with the Earth. The Earth got tiny bit slower, but the difference in mass is so great I don't think we noticed. But thank you, Earth. It was given a little bit more kick, and actually it went off to Mars and got a bit of a kick from Mars, came back to Earth, did that again, got a little bit more of a kick, and that helped us head out into the solar system. So playing kind of interplanetary billiards.
I think it's probably time to turn it over to the audience for some questions. So this is the engineers, spaceflight engineering from the BBC World Service. We've been exploring putting robots on Mars, launching geostationary satellites and landing a probe on a comet. Later we'll talk about the future of space travel and the politics of space. But before we go there, who has a question on anything we've covered so far? Let's have a look. Yes, and just about 4 rows back there, just there. Thank you.
Hello, yes. When things go wrong, is it possible to find out what went wrong and how it happened, or is the evidence just unobtainable?
I'm actually going to send that first to David because of Rosetta. Now, Rosetta, our mission to the comet, famously was very successful, got in and around the comet, did a lot of work, but the probe got onto the comet, fell over, was out of the sunlight, so couldn't operate solar panels. Now, I always think, if I'd flown halfway across the solar system, I would take a lie down in the shade when I got there. But that's a good question for you. How easy is it for you guys to find out what went wrong in a mission like that?
Well, generally speaking, there's a tremendous amount of data being acquired aboard the spacecraft all of the time, and we can relay that back often in real time whilst things are happening. So Rosetta, in that case, the Rosetta spacecraft worked beautifully, but it actually recovered during its journey of 10 years. Not everything went perfectly well. There was some leakages in some part of the propulsion system, but we knew that was happening. We were able to compensate for it. There are devices inside the spacecraft that help control which way it's pointing, wheels that are turning continuously. Some of those were starting to get a bit sticky they were starting to show some noise as it was flying along. So we had the backup ones back in the lab. We did some more testing. We understood what we had to do to get them a little bit hotter, a little bit warmer to keep them cozy, and it all worked fine. In the case of Philae, the harpoon didn't work.
Thank you. Okay, our next question.
Hi, thanks so much for coming here tonight. A question about the geostationary. I'm curious, when the onboard engines run out of fuel, do you find a way to bring debris back down? And more of an international question, are each agency looking in ways to recycle things that they've sent up or deal with debris that's currently up there at the moment for future projects? Thanks.
The question is, what do you do after the life?
So yes, when the satellite has run out of its onboard fuel.
Actually, it is very important that at the end of life, we have to ensure that it doesn't remain there anymore. In case of geostationary orbit, it takes many, many, many years for it to come down on its own. Therefore, you have to save certain amount of fuel in the satellite so that it is at a calculated period of time when its operational life is complete. You have to fire those thrusters and take it away, at least 200 kilometers away. We call it as a graveyard orbit.
Thank you, Anu. And we had a question just behind there. Perhaps we can have one for Adam, otherwise he'll feel left out.
Thank you. I'm interested to know that as engineers, I'm sure you've done the calculations and it's very dangerous to go into space, but nevertheless, would you like to go anyway?
This really is a question for Adam. So, it's very dangerous to go into space. Would you go anyway?
No. It is very dangerous. I think humans venturing out into space is actually very important. I think when we engage in this active exploration, it's kind of a gesture of our humanity, really. It's akin to a performance art, the art of the possible. What is our species capable of doing? And so I think it is important that humans are involved in exploration and space exploration. I have sweet children who I love, a beautiful garden, and I prefer to stay here.
David?
My answer is dangerously similar, but last time we had a call for astronauts to the European Space Agency, we had 8,000 applications. We ended up with recruiting a group of 5 extraordinary human beings, and we could have had many more that are equally a high standard, and having all of those, knowing all of those people now, they're all a much cleverer and more capable of doing the job than I am.
Anu, would you go to space if you could?
Oh, I would have loved to.
Well, thank you. So there we must take a short pause. We'll be back in just a minute to explore more about space engineering with Anuradha TK, David Parker and Adam Steltzner. You're listening to the BBC World Service. I'm Kevin Fong, and this is The Engineers Spaceflight. Welcome back to the Imperial College, London. We're here with our partners, the 1851 Royal Commission, to discuss spaceflight engineering with some of the world's leading engineers, Adam Steltzner, Anuradha TK, and David Parker. So far, we've been discussing the formidable task of launching and landing spacecraft and some of our engineers' greatest achievements. But what does the future have to offer? Now, I'm going to start with you, Adam. NASA's going back to Mars in 2020. Why? Why are they going back? We've sent so many things to Mars. We know so much about it. What's all this effort for? And what, if any, are the unique technical challenges of the 2020 mission?
Well, we ask the scientists of our nation, actually really global scientists, regularly. NASA asks them, what should we be doing? And we call that the NASA Decadal Survey. And most recently, they've said one of the most important things we can do is bring samples from Mars back to Earth. Because for all the ingenuity we might pack in a rover or a spacecraft, it doesn't match the ingenuity we have or the instrumentation that we have back here on Earth. So to really unlock the mysteries of Mars, specifically that mystery of life, the scientists tell us to bring samples back. It's a very difficult challenge. It takes 3 missions to do so. We're in a partnership with the European Space Agency to that end. But the first of those missions is a NASA mission, Mars 2020, and I'm the chief engineer. We're going to drill into the rocky material of Mars and take core samples of rock and regolith for return to Earth. They must be absolutely sterile, clean of any Earth contamination. We don't want to get the samples back here on Earth and find, mysteriously, the common cold virus exists in Mars. So, the architecting, the designing of that sampling system to take, seal, and keep clean these samples robotically millions of miles away, it was the central challenge of our effort.
I do love that idea that this is a mission that's going to go up and sort of take these samples and just leave them in a carefully marked location for another mission to follow up on.
Yes.
It does seem like only half the job being done, Shani.
Fair enough. It ends up being that we humans don't yet have rockets big enough to put all the equipment we'd need to do it all in one fell swoop. So we need to break the challenge up into pieces. Also, the budgets of our various countries can't really afford to do it all at once. So we break down the engineering challenge into separable elements to be able to complete the first element, to know that you've got, for instance, samples waiting for retrieval on the surface of Mars. That makes the investment for the second one easier, the effort for the third, etc.
And I guess this is part of where the international effort and partnership comes in. David, what role will ESA play in these sample return missions?
Well, we're planning to play an important role. So Adam talked about 3 missions. The second mission would be a NASA lander to go back in 2026, go to the surface, and then deploy a small, fast rover, a European rover, that would go out and collect these samples that have been left behind by the 2020 mission, bring them back, put them into a container the size of a football, launch them back into orbit around the red planet. So the first attempt to launch a rocket from another planet, a rocket that we've had to take with us, come back into orbit around the red planet, where a further spacecraft, hopefully to be provided by Europe through the European Space Agency, will be in orbit, controlling all of this, providing telecommunications and all the rest of it, and then to capture this interplanetary football, seal it into a return vehicle to be provided by NASA, bring it all the way back. So the first spacecraft to make the round trip to Mars.
And when we're talking about moving things between planets, so far the things we've talked about use fairly conventional propulsion systems, using solid and liquid fuels to get them on their way, and these sample returns would use similar. But actually there are other types of propulsion, aren't there? And ESA's mission to Mercury has used a rather exotic system, electric propulsion. Tell me a bit about why that is useful or necessary, and whether or not we're going to see more exotic propulsion systems in the future.
I think we do. We certainly will. So Bepi Colombo is the mission to Mercury, another multi-decade project launched October 2018. It'll make the most complex, sophisticated survey of a very mysterious object, Mercury, an anomaly in our solar system. To get there, we'll do several of these interplanetary flybys we talked about also, but it also has the most complex, most challenging electric propulsion system. What's that? We convert, instead of using rocket fuel, burning things, we convert solar energy into accelerated ions, accelerated to enormous velocity. We break down xenon, small amounts of xenon we carry aboard, accelerate that, and that pushes the spacecraft. Incredibly small amounts of thrust, fractions of a Newton, so you'd need several of these just to lift yourself off the ground. But they use incredibly small amounts of fuel, so they're super efficient.
It's all about better mileage, isn't it, in the end? Yes. Anu.
Yeah, this is what is being thought of and already used in some of the geostationary satellites too, that instead of having engine, a small engine on the satellite to take it to the geostationary orbit, you can as well use the electric propulsion systems. Just a small amount can give 4 years of station keeping.
And most, electric propulsion sort of exploits that idea that in space there is no friction. So if you give a little bit of force and you keep giving a little bit of force, things keep accelerating. And so, that's why that system wouldn't work anywhere on Earth or in Earth's atmosphere.
You could never use electric thruster to get off the surface of the Earth into orbit, but they're very useful for all sorts of purposes, flying satellites very close to the Earth where there's a lot of atmospheric drag. And it's great to see these engines becoming really used a lot. The engine for Bepi Colombo were actually designed in the UK, and for me it means a lot personally because my father was involved in these engines very, very early stage as a physicist 50 years ago. At the time of the moon landings, I remember him getting involved in this work, so it's great to see them being used for real now.
And we're talking about your work with geostationary satellites. But of course, Elon Musk and SpaceX have told us they've started work on their ambitious SpaceLink project, which will be a network of satellites that he's going to put up in low Earth orbit to bring internet access to every part of the world. And you think this is a great idea?
In fact, this is one of the companies which is bringing in. A lot of people are thinking of bringing these small satellites which can be at a lower Earth orbit. There are two reasons. Now, geo orbit itself is totally crowded. I think somewhere between 1,100 to 1,400 satellites are there in the orbit, and many of them are old satellites which are dead, which are there, and you're not getting a place to be there. The orbit spectrum is an issue. And secondly, the turnaround time. There are also a lot of fears that what is going to happen at the low Earth orbit with so many satellites, and are we reaching a point of Kessler effect? So we need to look at that. And also it is not easy to maintain. Continuously it is a production of satellites have to be happening. The life of the satellites will be less and you have to keep replenishing them. And when you're using it, you need to have coordination with all the countries. It's a low Earth orbit, so it's a different ball game, and we need to watch and see. So the worry is too many satellites around the globe.
But it is nevertheless attractive, isn't it, to everybody to want to have internet the world
Yes,
over wherever.
look, it is looking very attractive. We have to see what are the practical difficulties.
Is there another way of doing it, other than having this sort of net of satellites so close to the Earth, the way Elon Musk is suggesting?
See, one more thing is what we have to look at is why do we need such low latency?
And when you say
So,
low latency, you mean?
What I mean is, if I send a signal to the satellite and get it back, it is taking a turnaround time around 500 to 600 240 milliseconds, 250 milliseconds. Physically it requires, and then your electronics delay, etc. So why is that a botheration? Normally we don't even notice that, but today we are talking about some of the applications like Internet of Things and having cars which are being driven without a driver, so that you need to have a very immediate information. So do we have to do it with a satellite, or can we have terrestrial systems to aid for it? These are some of the things practically we have to look at.
ESA's currently collaborating with NASA in developing Orion, the crewed spacecraft built to go beyond Earth orbit for the first time in nearly half a century. What are the plans for that vehicle, that system?
Yes, we're looking to try and get outside of low Earth orbit. It's been a while, as you mentioned. Orion is a vehicle that we're developing with a propulsion system provided by ESA to allow us to get out of low Earth orbit and to the moon and possibly beyond, and put human footsteps on the surface of Mars someday.
And David, Orion is part of a plan to extend our reach in space back to the moon and beyond. But ESA's also talking about getting involved in something called the Space Gateway, which should be an international project. Now, these are sort of key components of what I like to think of as the second space age. A vehicle that can go beyond low Earth orbit, carrying astronauts, and this Space Gateway, and it's intriguing. Tell me a bit about that.
Yeah, Kevin. So we're entering this second era of human exploration beyond low Earth orbit, and I like to make the comparison with the race to the Antarctic more than 100 years ago, and we went to Antarctic 1912. But some people made it back, some didn't. But at the end of that, we forgot about the Antarctic. Then 40, 50 years later, we established permanent scientific outposts. The scientists work the Antarctic all the time now, and for all sorts of areas of science, including discovering the hole in the ozone layer. So it's not about going back to the moon, it's going forward to the moon, in the sense of not just making a quick round trip, but doing the science that can be done there, working out how we can use the resources of the moon to support exploration. And as part of that, the idea is the Lunar Gateway. The Lunar Gateway would be our spaceport around the moon, allowing us to control robots, but also be the place where we bring together all the pieces of technology to land on the surface of the moon, bring the astronauts back. It'll be uncrewed some of the time, doing great science around the moon, and when the Orion vehicle turns up with the astronauts, they transfer over to the human lander and go down to the surface. And these are the plans we're working on with the international partners right now.
And Space Gateway is intended to be a sort of space station of sorts that sits at this kind of balancing point between the Earth and the Moon, so that you can launch expeditions to any number of destinations.
Well, it's again, we've talked a bit about orbits, but Gateway will be in a very unusual location. It's actually in orbit around the Earth, but as seen from the Moon, it appears to be in a polar orbit. I'm not going to explain the physics of it, but it means that from its location, you can always see the Earth, so it's great for communications. It can cover 85% of the surface of the Moon, and what's more, you can control and see things on the far side of the Moon. And so we're particularly interested scientifically to explore the far side of the Moon. Why? Because there's a big hole there. The South Pole Aitken Basin has extracted the interior of the Moon, and we haven't explored that yet. So for all of these reasons, we need an outpost around the Moon to support our robots and our humans.
Thank you. This is the Engineers Space Engineering. We've been exploring spacecraft, the practicalities of launching them, difficulties of landing them, and what the future holds. So I'm going to turn it over to our audience to see if there are any questions for our spaceflight engineers. Thank you.
I'm Samantha. How long do you think it will be until commercial space travel?
Thank you. How long do we think it's going to be before we see commercial space travel? I guess for people, for astronauts. Adam, what do you think?
I suspect that you'll see the first space tourists. Their time in space will be short, but I think you'll see that within a year or so, honestly. I have friends who told me it was going to happen last year. So, commercial space travel for tourists or for civilians wanting to just go and see, I think, in an orbital or suborbital sense, will happen quite quickly. How long it will be before you're able to go to the moon, that's a tougher question to unpack, and I'll pass on trying to figure that one out.
Thank you. Another question, please.
What would happen if evidence of life was discovered on Mars?
Ooh, small question. What would happen if evidence of life on Mars? I have to go to our Martian, Adam. Adam, what would happen?
Well, I was going to say that may be a question for a philosopher more than an engineer. There's something called the Drake equation. If you take the number of stars and you multiply it by the probability that the star has a planet, which we used to think was quite small, and the Kepler mission has demonstrated is not what we thought. It's many more of the stars that we look at have planets beside them. And then you look at the number of planets that are in the habitable zone, that is a zone in which liquid water can exist, and so forth. And you ask the final question, what's the probability that on a planet that can survive and suit life occurs? That's a guess. But as long as that number is not absolutely mathematically zero, the Drake equation tells you that there are other things alive out there in our universe. one of the most captivating questions, of course, is could they be on one of their nearest neighbors? Could Mars? So if we find evidence for life on Mars, I personally will be relieved. Because the notion that we are the only living things in this universe is terribly frightening to me.
Anu, one of ISRO's missions is looking for methane traces on Mars, and methane possibly is a sign of life. Tell me a bit about that.
True. Methane is something which gives a indication that there is life. Okay, could be life, even bacterial or that kind of form, which can generate the methane. So that is why there is a lot of hope that we find positively that there is some methane, and then link it. Why is it there? So whether there is any life. So that's one of the basic things for the life one looks for.
And David, I mean, as someone involved in senior strategy at ESA, what are your thoughts about this? What happens if we find hard evidence of life on another planet?
Well, my best guess is with Mars we won't find extant life, but the challenge that we've taken up with our ExoMars mission right now is to try and see if there's methane there. Okay, it might be active life, but more likely active geology on the planet. But we're searching with ExoMars rover that we're launching next year to explore the planet 3.5 billion years ago, because we're going to explore an ancient seabed. And the point is that life got going on this planet 3.5–4 billion years ago, as far as we can look back. So if we find any evidence of life 3.5 billion years ago on Mars, bingo, in the sense that Drake equation point, that this probability goes dramatically up if two similar planets got life going at roughly the same time. Then we start to put those numbers into all of the planets we're finding around all of the other stars all of the time. But of course, the question is the life seem to have the same characteristics. So one of the characteristics of the amino acids is they're handed. They're either left-handed or right-handed. Are they of the same handedness when we go to another planet? So that will tell us, does the life have a common origin or a separate origin, for example?
Thank you, and which leads us on to another question from our audience.
Hi, good evening. Sorry to drag this down into politics, but the current sitting US president has redirected NASA's focus from Mars back to the moon. So to what extent is going to the moon a necessary step in getting humans to Mars?
I'll
Either of you two want to take that?
I will spin that out to David.
Okay, so I always do this at these events, and it doesn't work on radio, but I'm holding my hands together as if they were a ball, that representing Earth. Space station is the length of the hairs on the back of my hand above the Earth. The moon is in about the fourth row of this lecture theatre. Unfortunately, Mars is somewhere back to Paddington Station, where I arrived earlier this afternoon. Each step is 1,000 times. And right now, even if we can build a rocket to go to Mars, the astronauts, they wouldn't survive the journey. We don't know how to support them, protect them from the radiation, to support them with the food, the water, all of the supplies they need to get them back there and back in one piece. So the moon is our black backyard for learning and developing all the techniques we need to go to Mars, in my view, to prove safely we can make that journey. I think it would be unrealistic to imagine we make that single leap to Mars right now.
Front row here, just down on the left. Thank you.
I'm William Day. On the journeys to Mars, when and if humans go to Mars, how can they bear with each other? Would they go insane?
On a journey to Mars, how will the crew bear the company of one another? With conventional propulsion, it's about 6 or 9 months in each direction to Mars. Who wants to take that one? And Adam, go for it.
Yeah, it is challenging in general. There's, I don't know, a few hundred people in this audience. If we were to randomly select from all of us here in this room, whatever the number of crew, we would absolutely be unsuccessful. You need to select your people very, very carefully. We've sort of proven in closed quarters and submarines and other settings that you can choose a set of people who won't just be at each other's throats for that duration, but it is a substantial challenge, and the psychology and the psychological makeup of a crew is essential.
We've got time for another 2 punchy questions and punchy answers. So, Peter, yes, thanks.
Hi, I was wondering, how do you make a breakthrough as an engineer?
How do you make a breakthrough as an engineer? Anu, how did you make your breakthrough as an engineer?
It's not tough at all. I mean, it goes by your interest. How will one break through as a musician or an artist or an engineer? It is your basic interest. For example, I was always interested in maths and science throughout, and engineering was my first choice because I could pursue that. And application-oriented maths and science is what I liked. And it goes by your interest. It's not difficult if you're interested in.
And Anu, when you studied engineering, what was the makeup of your faculty like? Was it an equal mix of men and women, or was it mostly women, mostly men?
No, when I passed out, that was dinosaur era. 1982, I passed out. And at the time, we were 10 girls and I think 60 boys in the class. So that was a kind of ratio. But my daughters, when they studied engineering, it's 50% girls and 50% boys. Yeah.
And a last question from our audience. Peter, where do you want to go? Thank you.
Hi, my name is Gren. It's great that we're making rockets reusable and more powerful, but at the end of the day, it's still a very messy and primitive way of getting stuff into space. When can we come up with something better?
When can we come up with a better and less messy way of getting into space? Adam, that's one for you.
Yeah, well, so I agree. It is messy. The very act of taking something from Earth and getting it into space is very energetic. You put it, if you think of the energy that something has in orbit, you have to put that energy into the device. And sometimes, especially in engineering, actually one of the features I love about engineering is that it ultimately must be practical. The solutions sort of must pass the practicality test. Will it really work? So we hate propulsion as you see it today. There are ideas, but they currently, as we understand it, as I understand it, and I think it's likely to be the case for the foreseeable future, rockets are the least unacceptable way of getting something into orbit. Things like rail guns, accelerating really quickly down here on Earth, great, except now you're moving orbital speeds down here on Earth, and that's also very messy. That's a lot of atmospheric drag. So we're always looking for a better way, and I don't think I'm unaware of anyone out there that's waiting for us.
So, Anu, I guess part of this question is perhaps about the possible technology of space elevators, which involve geostationary satellites and orbits. What do you think about that possibility, that there may be a better way, that perhaps we could get an elevator into space? What do you think of that?
What Adam said is right. We are all looking for better ways all the time, how to go. Today we are where we are. We have to take through our rockets. There's no other way at present.
David?
I have some hope that the technology that combines a rocket engine with an air-breathing engine technology, something that's been worked on for a long time and is now becoming physical reality on test beds in Europe and in the US, could create the machine that goes down a runway and goes directly into space and comes back again. And I don't think that's so far away.
Thank you. And that is it for the Engineers Spaceflight. From Imperial College in London, on behalf of the BBC World Service, our partners, the Royal Commission for the Exhibition of 1851, and my producer, Charlie Taylor, please join me in giving a warm round of applause to our fascinating engineers, Adam Stelzler, David Parker, and Anuradha TK.